Okay, so let's continue our exploration of the abalone dataset. So where we left off last time was we made a bunch of different scatter plots of the various physical measurements versus the age. Okay, and so to remind ourselves, here's where we ended up, and we ended up with a figure like the following, where each subplot is a different physical measurement on the x-axis and the age on the y-axis. And we noted that while there is a general positive correlation for most of these measurements, it's pretty messy. Okay, so one of the things that we can do is use a different type of plot in order to further explore this data. Okay, and so in particular, you might make the hypothesis, knowing something about animals and how animals grow, that perhaps there's a difference between the way that male specimen of abalone grow versus female specimen. This seems like a very sensible thing to do. Okay, so since we have that information also in our data set, we're going to try to figure out if there's another way we can look at the data that's a little more illuminating. Perhaps it will pop out. Okay, so what we're going to do is I'm just going to pick one particular set of data, and it's the shucked weight, which is going to be the fifth column of the data set, right? So shucked weight right here in the fifth column. And you can do the same thing with all of the other ones, but I'm just using this for illustration purposes. So what we can do is we're going to try to separate out the individuals and their shucked weight by whether or not it's a male or a female. And I'm just ignore the infantile ones for now. Okay, so what we're going to do is, if you consider your X matrix, right, it is a large matrix, kind of like the following. Here's my X matrix, right, where here each row is an individual and each column is a measurement. Okay, so what we can do is, if you think of each row as an ID, right? So each abalone for which this data set have been collected has an ID, and it counts from 1 to 4177, right? Now, what we want are the IDs of the individuals that happen to be male and that happen to be female. So if we look at the gender, if we look at the gender vector, we see that it is a long list, a really tall list of M's and F's and I's. Okay, so it is the same size as my X vector. So it's the same height, right? And then each of these entries is either an M or an F or an I as a letter. So what we want to do is find the indices of the gender vector that equals F or equals M. And that will give us the individual IDs that are male or female. Okay, so I'm going to show you how to do this more specifically. And what I'm going to do is I'm going to now find a vector of IDs of all of the male individuals of abalone. I'm going to do that by saying find where gender equals M. Okay, and then females equals find gender equals F. Okay, now what this is going to give me are the IDs of all the rows of X that correspond to males and to females. So I'm going to keep that list. So I have two populations now, all the male abalone and all the female abalone. I'm going to try to separate those out. Okay, so the find function is really useful because it returns those indices where that condition inside is met. So inside what we have is a conditional statement, right? So it's going to go through every single entry of gender and ask the question, is this entry of gender equal to the letter M, right? And if it's yes, then I'm going to keep that index, and if it's no, it's going to throw that index away. So I end up with a list of indices of males and a list of indices of females. Just think of them as, subject ID numbers or something, which corresponds to all the row numbers. Okay? So then what we're going to do is we're going to do the same scatter plot as we did before, but we're going to, let's say, use two different colors and different marker sizes for the males and females and see what we get. So remember, to do that, we have to do a hold on the figure, otherwise the second figure will override the first figure and you'll only end up with the most recent thing you plotted. So we'll plot S weight of all of the males by the age of all the males. And we're going to make those, let's say, blue circles. Oop, that's not where I want it to be. Here we go, blue circles. Blue circles, here we go. And we're also going to plot the S weight of all of the females by the age of all of the females. And we're going to make those, let's say, magenta triangles. Okay, let's see what that looks like. Here we go. All right, here's my scatter plot. On the horizontal axis, we have the shucked weight of the abalone in grams. On the vertical axis, we have the age of the individual in years. And in blue, we have all the females, and in magenta, we have all the... Oh, I said that the other way around. The blue are all the males, and in magenta are all the females. And so in order to not confuse ourselves, like I just did, we are going to label our plot, right? So the x-axis is shucked weight in grams, and the y-axis is age in years. And we have a legend, which is males versus female abalone. Okay? Here we go. That's a little bit better, right? This way we are not going to confuse any of the viewers, and the viewers include ourselves. You write a lot of code, you end up plotting all kinds of things, so it's really nice to label your plots so you can keep track of what's going on in your own head. All right, so here we have shucked weight by age, labeled by color, and also by the shape of the markers by males and females. Now, unfortunately, sometimes you try things and it doesn't work out, right? We were hoping that somehow this plot would be more illuminating if you separate out the males and females, and in this particular case, I'm not really sure that happened, okay? It looks just as messy and confusing, and these two distributions are right on top of each other, okay? However, there is a weakness of this way of looking at the data, which is that when you have a lot of markers that are right on top of each other, like this, in this region right here, there's just a lot of dots. There's a lot of circles and a lot of triangles. It's hard to see exactly how many there actually are because they're right on top of each other, right? If there's 10 on top of each other versus 100 on top of each other, it'll look exactly the same in this plot. And so this way of looking at the data is actually not very illuminating for that reason, because it's actually kind of confusing, and I think obscures some of the features that may be present in the data just because of the way we plotted it. So what we're going to do is talk about a different way of plotting this data called the histogram. Okay? So a histogram is an interesting beast, and it's super useful, especially in exploratory data analysis. So in case you're not exactly clear on what a histogram is, it's actually pretty simple. So you start with a bag of numbers. Okay, so in this case, it would be one of our columns of X. Let's say, pick one, height. Okay, we have a bag of numbers, which is the height of all of the abalone that I've measured. Okay, now what I'm going to do is that I'm going to make a couple of buckets. Okay, and I'm going to specify what size the buckets are. So let's say that the range of my height is from 0 to 5 millimeters. I just made that up. I don't know if that's true or not. So let's say that I have a from 0 to 1. That's one bucket. I have another bucket that's from 1 to 2. I have another bucket that's from 3 to 4, 4 to 5, and let's say another bucket from 5 to 6. Okay? Does that make sense? Yeah. So this is the between 0 and 1, 1 and 2, 2 and 3, 3 and 4, and then 4 and 5, these buckets. Okay? Now I'm going to take my giant bag of numbers, my thousands and thousands, if not tens of thousands and millions of numbers, and I am going to throw them into these buckets depending on what values they are. Okay? And then what I'm going to do is I'm going to make a bar graph whose height at each of these buckets corresponds to how many numbers ended up in that bucket. So maybe I had a few numbers that were in this bucket, maybe most of them are over here. I have a few more individuals that are whose number is between 1 and 2, maybe a few more of these, maybe that many of those, and something like that. Okay, so the x-axis here is going to be the measurement, and the height of the histogram is something like abundance. Okay? How many there were in each of these buckets. Okay? Now, I've just told you how to construct it, and you can write some code to actually do this and plot it as a bar graph. But it turns out more expediently, this is a built-in function. And it's called the histogram function, which is a pretty useful function in exploratory data analysis. And I'll show you how that works. We are going to make a histogram, just like this bar graph of buckets here, by using the histogram function, which is really, really useful for exploratory data analysis. So we, like above, we're going to make another variable called sweight, which contains all the numbers in the 5th column of our data matrix X. So this is the shucked weight of all of the abalone. And we're going to make a figure, and we're going to construct a histogram of sweight. Okay, so let's run that. And here's what we got. This is our histogram. So on the x-axis is the value of the measurement. So remember, these weights are in grams. And so the variety, this is a distribution of different individuals of abalone that they were measured in the data set. And they range from quite light to pretty heavy, 250 grams, which is pretty weighty. So that's good. And this tells us the relative abundance inside each of these bins, which is pretty useful because it was really hard to tell this information from the scatter plot because we had markers that were literally right on top of each other, and it was really hard to tell how many of them there were. Okay, so now what we can do is try to do the same thing. We're going to put a hold on here, and we're going to try to plot the histogram of the males and the females separately. So S-rate females. Here we go. Okay, so just like before, let's add in our legends so we know what we're looking at. Again, the X label is shucked weight in grams, just like before. The Y label is now relative abundance, so let's call it that, like, or number of individuals in the data set, right? And then the legend, like before, we have males and females. Okay, so now we have a properly labeled graph that we can look at and make more sense of. Okay, so here are the histograms. And like we suspected from plotting the scatter plot, they are right on top of each other, right? So the males and females really do not separate at all. There appears to be no systematic difference in terms of shucked weight for males and females, because they're just as likely to be any one than the other. But here is a more quantitative way of looking at this information, and we know that these two distributions are now lying on top of each other. They're not really all that separable. We can then go ahead and quantify things like the means and medians of each of these distributions and compare them. But you can actually tell a lot just by looking at the data. And this is why I'm such a big fan of pretty extensive plotting and exploration of the data before I even start doing kind of quantitative analysis. Because I can tell by just looking at this plot that even if you computed the mean, the standard deviation, and all of that stuff for these two populations, they're probably not going to be all that different just by looking at it, right? There might be some small differences you might be able to tease apart, and it may or may not be significant. But the bottom line is, if it's not visually obvious, then you're going to have to work pretty hard to tease out the differences, even if it does exist. And so that's one of the reasons why plotting the data extensively before you're looking at it is sometimes a good idea when you're starting to look at the data set. And so histogram is a really good tool. Scatter is a really good tool. I'm going to show you one more tool that is a built-in function that's really convenient to explore data, and that is the scatter command. Okay, so what the scatter command does is that it plots a scatter plot. When you're asking yourself, well, I already know how to do a scatter plot, right? I can use the plot function and make dots. this is true. But the scatter function has a couple of nice features, which is why I still use it sometimes, because it makes it really easy to do a couple of different things. Okay? So the scatter command starts out just like the plot command, where let's say that I have two things that I want to plot. Let's say I want to look at the length versus the diameter. Okay? So length is the first column of x, and diameter is the second column of x. Okay? And I'm going to call it a scatter function, and it starts out just like the length of the plot function, where I could give it the list of x coordinates and the list of y coordinates. Okay? But that's not all. It also allows you to specify in two additional parameters the size of the marker as well as the color of the marker. Okay? So what we can do is say, let's actually specify the size of the marker to be proportional to the age. And we can also scale the color of the marker to be proportional to age. Okay? So let's see what this does. Here we go. That's the plot right here. And the dots are a little bit small because we have a lot of dots. Okay? What we're looking at is length on the horizontal axis, diameter on the vertical axis, and there's some small dots down here that are darker blue, and they correspond to the young individuals. And there's kind of a cloud up there where we have some larger circles that are of a lighter color, and that corresponds to the older individuals. And so this is a really convenient way of making a plot like that in a quick way without, I mean, you could have done all of that with plot, but it would have taken you a long time and a lot more code. So scatter is a really good way of doing that. So this is another way of just looking at the data really quickly and seeing if there's anything visually obvious. And anything visually obvious will usually become a good candidate for further analysis. And in this case, I'm looking at it, and yeah, there is definitely a positive correlation between both the length and the diameter, and between each of those measurements and age. But it's probably not something that I'm going to pursue because it looks like this is a generic sort of correlation, and it's probably not going to turn out to be anything terribly interesting. But the fact that I plotted it makes it so that I knew that pretty quickly, and I didn't have to run a bunch of analyses in order to find that out. And so that's the power of plotting.